This is a story about the effects of slow diffusion transport and how they can change the mechanism of barrier crossing in nucleation. And the goal here is really to understand how it is that so many people are reporting that they see characteristics of two-step nucleation in systems that don't have the metastable fluid-fluid transition that was used to explain it in the landmark paper of Frenkel and Tinwald. So there are a lot of systems now, for example, glycine, methane hydrates, calcium carbonate, very different chemical systems where people have all pointed for various reasons to this two-step nucleation theory being present. But the two-step nucleation theory, of course, requires this short range attraction between particles with relatively large diameters, and that gives rise to a special phase diagram. And this was really the story put forth by Frenkel and Tinwald for the first time back in 1997, and a beautiful landmark paper. And I think that to understand this talk and why it's interesting, you probably should be familiar with that work. So with that aside, let me go on to tell you about where we got interested in this. We were trying to do some simulations related to solid state precipitate nucleation processes, and the concentration fluctuations take a very, very long time to decay, and I was worried about how we were going to integrate those out so that we got the nucleus size as being the only important variable in accordance with the nucleation theories. And I realized, if the concentration fluctuations take so long to decay, that they're actually comparable to the time that it takes to cross over the barrier, then they're actually potentially an important part of the mechanism themselves. And so this is really where this story begins. So actually, I'm not the first person to think about this. K.C. Russell at MIT back in 1968 thought about this problem as well. He said, by definition, the critical nucleus is an unstable equilibrium with the surrounding matrix. Successful promotion is possible only if the material added to the cluster is replaced from another part of the matrix. So we've got a mass balance argument here. And he goes on to say that a proper analysis of nucleation in condensed phases should therefore consider not only cluster sizes, but also the concentration in that nearby matrix. And this is basically the spirit of our model. We're going to develop a model that actually incorporates these ideas. And I want to specifically develop a model that's still based on classical nucleation theory, because what I want to do is to be able to understand how does slow diffusion transport impact a process that would otherwise be described exactly by classical nucleation theory. And it may not be at all obvious, but actually that model looks like this. Okay, so we have a nucleus of size r, a radius r. We have slow diffusion transport out in the bulk, and these two things communicate with each other through their interfaces, right? So right here at the interface of the nucleus, I have mass transfer happening. If the nucleus wants to change size, it has to do so by mass transfer from the surroundings. So that's a fixed law kind of boundary condition here, fixed first law boundary condition. And out at infinitely far away from the nucleus, we're just going to assume that the concentration goes to the bulk supersaturation. But in the intervening, near the nucleus, we can have concentration fluctuations. But if it's true, then that we reverse the things and say that nucleus size actually becomes a slow variable, then we have an ostwald-freundlich boundary condition. And I will explain why I want to do that here in the next couple of slides. Okay. Computer stuck. Okay, so I'm going to refer to this model as a model of concentration fluctuation gating. Okay, so the reason for this is that Vollmer's classical nucleation theory, developed in 1926, was thinking about vapor condensation. Okay, so in the vapor, concentration fluctuations decay very rapidly. For example, there's no reason to think about slow diffusion transport to the nucleus because the mean free path for molecules colliding with other molecules in the vapor is typically much larger than what we would think of as being the diameter on the nanometer scale for a nucleus anyway. Okay, so So really, there's ballistic transport to the nucleus. Diffusion is not a factor in the gas phase. And because of that, you can ignore concentration fluctuations around the vicinity of the nucleus. You only have to think about the bulk concentration and the size of your nucleus as a function of time. Okay, so that's the basis of the classical nucleation theory developed in 1926. Now, everyone basically uses this same kind of thermodynamic framework in solution as well, right? So when I say the same thermodynamic framework, I mean that we keep the nucleus size variable as an important variable. We think about the free energy barrier as a function of nucleus size, and we ignore the probability of different kinds of local concentration environments around that nucleus, okay? So we are actually told in many papers, and I've done this as well, basically the entire literature is full of claims that you can basically take the description of vapor condensation, where you have a vapor in a liquid phase, and you can just replace them with dilute and concentrated regions in solution. And so this is the basic idea, and it's perfectly thermodynamically correct, except that we may be looking at the wrong variable as being slow in certain cases. And let's quantify that argument. So if you think about the typical size of a nucleus as being on the order of a nanometer or so, and you divide by now the liquid phase diffusivity, so if this nucleus is a solute nucleus coming out of solution, those solutes have to diffuse to the nucleus. And the time scale that comes out of that is this ratio, length scale squared, divided by the diffusivity. And for a typical solution of, say, aqueous solution, small molecule diffusing, you have a diffusivity of 10 to the minus 9 meters squared per second. And when you take this ratio then with a nanometer plugged in here, you find that this is on the order of nanoseconds time scale. So this is actually a very long time compared to what we typically assume for the attachment and detachment time scale. If a molecule is sitting right next to the edge of the nucleus, it can attach and detach many times, many times in a nanosecond. And so we would say that the attachment and detachment time scale is on the order of picoseconds then. Well, if it's true that these two things are so lopsided now in the other direction, so now the fast time scale is attachment and detachment, no longer have this ballistic transport like we did in the gas phase. We have to diffuse back and forth, but the attachment and detachment is happening over and over and over again from molecules in that first shell. Then that first shell concentration is going to be quasi-equilibrated to the equilibrium value that would exist in contact with a nucleus of fixed size r, right? So the nucleus really can't change size for a very long time until molecules can diffuse to it from the bulk. But while it's waiting for that to happen, the molecules at its surface can attach and detach over and over and over again, and they will continue to do that until the first shell concentration equilibrates to that basically frozen average nucleus size. Okay, so this is the thinking. And what this thinking does is it reverses what we have to consider as our slow variable. Now, nucleus size is effectively slaved to the surrounding concentration field. And what does that do? That gives you the model that looks like the one that I showed on the first page. Okay, so nucleus size is a function of time. I have slow diffusion transport that governs the rate at which things can arrive at my nucleus. I have a mass balance condition that says that what goes into increasing, what attaches to the nucleus to increase its size must be something that's being pulled out of solution according to a concentration gradient. And we have this boundary condition that reflects this third bullet point here. The ratio of these two timescales says that the local concentration will be in equilibrium for an object of size r, right? So this is basically Ostwald-Freundlich equation. We've seen this all the time in the context of ripening. And basically, this is the nucleus size in here. If the nucleus size happens to be the critical size, it's an unstable equilibrium. This term becomes 0, which makes my whole exponential turn into 1. E to the 0 is 1. And the concentration in equilibrium with that critical nucleus size is the bulk supersaturated concentration. But if I make my nucleus size much larger than that bulk concentration, this exponential term then eventually goes to the saturated value, and that factor e to the minus beta delta mu then just converts this bulk supersaturation into the saturated value. So at macroscopic sizes, the concentration in equilibrium with that nucleus becomes the saturated value. At very, very small sizes, of course, it has to be much, much larger than the bulk supersaturation in order to sustain a nucleus in that environment. Okay, so this is the basic idea of the Ostwald-Freundlich equation. And notice that we're not using this in the context of ripening here. We're using it in the context of nucleation, and it becomes a boundary condition for the interfacial concentration right near the surface of my nucleus. Okay, so how does this model play out, and how is it possibly a model for nucleation? Well, classical nucleation theory says that the free energy barrier for forming a nucleus of size n is given by this. We can make a number of substitutions here, basic elementary definitions that I've covered in other papers and talks. So the driving force is related to the bulk supersaturation, and that's the formula for this thing. I know that I can relate the number of molecules in my nucleus to the radius of my nucleus by just equating the volume formulas. A little less obvious is this idea that goes back to Vollmer and Weber of defining a size-dependent chemical potential. And that size-dependent chemical potential reflects the concentration that would be in equilibrium with a cluster of a certain size n. So we have a size-dependent concentration and also a size-dependent chemical potential. You get that expression by taking the derivative of the free energy, this formula up here, with respect to nucleus size, and you find that there's a bulk term and there's also a surface contribution. Okay, so now we equate that to kT times the log of the ratio of the concentration that would be in equilibrium with a nucleus of size n divided by the bulk supersaturated concentration now. Remember, when I have the critical size plugged into this formula, it's an unstable equilibrium, so these two things have to be 1, and that chemical potential at that point is then going to be 0. Okay, it's an unstable equilibrium point to have a critical nucleus in my supersaturated environment. Now what I'm going to do is just combine these expressions, and I'll leave it to you to think about how that goes, but it's just a matter of substituting everything into this expression and equating it to the thing that's over here on the other side, right? So we've got this expression, the delta mu naught becomes this thing, and the n to the minus 1/3 I can rewrite in terms of r, and what we get is this equation, which can be simplified by just remembering our definition of the unstable equilibrium here with my critical nucleus size, requires that I have C naught, the bulk supersaturated concentration, be this concentration at equilibrium with my critical nucleus size. So I'm calling that RCNT here, because the classical nucleation theory, critical nucleus size. And what comes out then is Ostwald-Freundlich equation, right? So probably to many viewers, this is not a surprise. These two things are based on exactly the same physics. So the barrier model that we use in classical nucleation theory is exactly the same underlying physical basis as the Ostwald-Freundlich equation. But here we are incorporating, so effectively what that allows us to do is to build a model in which classical nucleation theory enters as a boundary condition in the model. Okay? So now the advantage of doing it this way is because now I can think about that boundary condition, which contains all of the information from the classical nucleation theory, as being a condition that the transport processes happening on the outside, which classical nucleation theory always ignored, they can now be included in the description of the process. Okay, so there's some math coming here. Many of you probably will tune out at this point. I will try and make it quick and easy, but we have a scaled time and we have a scaled distance. And notice that my scaled distance is a time-dependent scale factor. My nucleus size is changing all the time, and so I have a moving boundary problem to deal with. We can get rid of that, but it's in exchange for dealing with some rather nasty nonlinearities in the equation. So just doing the chain rule, converting my variables from r and t into this scaled distance and scaled time, we recover a new differential equation and new scaled variables. This is my concentration field, and this is my nucleus size, written as sigma here. When we rewrite the ordinary differential equations. This is the differential equation that governs the nucleus size. It's really that mass transfer boundary condition. So this was the concentration gradient at the surface of the nucleus, and this was the size of the nucleus changing as a function of time. We also have a dimensionless partial differential equation that represents the concentration field changing around my nucleus, and these are my boundary conditions in dimensionless form. Okay, so in infinity, we have our bulk supersaturation, and at the interface, this is a dimensionless form of the ostwald-freundlich equation. Okay, so if this model really is consistent with the classical nucleation theory when we do not have concentration fluctuations, then in the absence of a strong concentration fluctuation, it should behave exactly as classical nucleation theory predicts, and that is indeed what happens. If I start a nucleus that is 80%, so smaller than the classically critical size, and I don't embed that in any special concentration fluctuation, then what happens is that the nucleus just begins to shrink, and as it shrinks, it creates this enriched zone, and that causes it to shrink even faster and faster, and eventually it blinks out. So this thing becomes, because of the nonlinearity here, it starts to shrink very, very fast as that nucleus gets very small. The driving force to shed particles starts to become extremely small. If I start this numerical simulation of these coupled differential equations up here, say at 120% of the classically critical size, then what happens is the nucleus irreversibly grows to macroscopic sizes. So this is indeed consistent with the classical nucleation theory when we do not have concentration fluctuations which are suppressed in the classical theory. So the same nucleus now, when I embed it in a concentration fluctuation, so this is now a zone of concentration that's enriched even beyond the bulk supersaturation. And the reason that we think that this could exist is because, of course, if you take a system that's supersaturated and you look at any certain observation window, and you ask, what is the concentration in that little volume right now? That's a fluctuating quantity. And it fluctuates around the bulk supersaturation, but sometimes it's higher and sometimes it's lower. Okay, so now imagine that you have a nucleus which finds itself in a region where the concentration is actually even higher than it typically is in the bulk. Okay, so this is this situation depicted right here. And what happens is that, again, I've started at 80% of the classically critical size, but you see that the nucleus grows. How is this possible? Well, what happens initially is that their mass transfer starts to take solutes from this concentrated region, and they start to diffuse towards the nucleus. As they reach the surface of the nucleus, they become incorporated. And as they become incorporated into that nucleus, the nucleus has to increase in size. And as the nucleus size increases, the ostwald-freundlich equation says that its surface concentration must drop. Well, if its surface concentration drops, that now creates even more driving force to pick up even more of the material from the surroundings. And so this nonlinear coupling between nucleus size evolution and the concentration field surrounding that nucleus can actually take a nucleus that the classical theory says should have shrunk and drive it across the nucleation barrier. And I would argue that this actually looks something like the two-step nucleation theory. You have a nucleus here that's embedded in a locally concentrated zone, and because of that locally concentrated zone is going to live for a while because of the slow diffusion transport. It can't diffuse away rapidly. While it's sitting in this concentrated zone, it feels like it's temporarily in an extremely supersaturated solution where the driving force for nucleation is very high. And that's why it's able to cross through this barrier. And once it happens and gets locked in, it basically is an irreversible transformation, and it's going to keep on going. So, fluctuations happen all the time. As I mentioned, if you look in any observation window, you see fluctuations that are up, fluctuations are down. And what you have here is evidence that concentration fluctuations that are actually enrichments, they facilitate nucleation. And just like gating processes that people have seen in enzyme kinetics and things of that sort, if there's a fluctuation that facilitates the transformation, and that fluctuation is always happening, then typically the transformation will happen when the fluctuating variable, for example, donor-acceptor distance, or in our case, local concentration, is in its favorable state, right? Is when it's enriched in the local environment. Okay, so you can actually quantify this for many different length scales and degrees of local enrichment. So I've multiplied these two things together because when you do that, these different conditions roughly fall on the same curve. And the interesting thing about this, you see initial nucleus size along the bottom axis, and you see degree of local enrichment along the vertical axis. Now, if the classical nucleation theory was correct, then all we would care about is nucleus size, and the boundary between nuclei growing and shrinking would be this vertical line passing through 1, right? That's clearly not the whole story. When you consider concentration fluctuations and their environment and their effect on the fate of these nuclei, you see that if the nuclei emerge in a region that is locally concentrated, they have a higher probability of they can grow from a point that would have previously been considered unstable. And of course, the converse is also true. If you have a large nucleus that emerges in a depleted zone, then it might go ahead and shrink back, even though the classical theory says that the nucleus should grow. But of course, these won't contribute much to the rate. If these fluctuations are going up and down all the time, then where nucleation will happen is when you're in this enriched environment, because it's easier here. I have to grow less of an interface between my nucleus and my surroundings, and some of the work is already done for me because I've moved the boundary between growth and shrinking over to smaller nucleus sizes. So I think this is kind of exciting. It suggests that the two-step nucleation theory can actually happen when you don't have a metastable fluid-fluid transition. And this, I think, provides a potential explanation for claims in the literature. For example, Meyerson's review article written back in, I think, 2009 says that two-step nucleation may underlie most crystallization processes that are happening in solution. And what do all crystallization processes that happen in solution have in common? Diffusion transport in the condensed phase is slow, right? And so I think that the reason that so many studies are pointing to two-step nucleation, even where we don't have this short length scale large particle attraction with the submerged critical point, with the fluid-fluid critical point, the reason that it appears that that's really not required is because this alternative route is really sufficient to give you something that looks kind of like the two-step nucleation scenario. So I guess the take-home message is that slow diffusion in condensed phases seems to be enough to favor a two-step nucleation pathway. And I want to thank the NSF Career Award for supporting this work. And you can see the original article is published in the Journal of Chemical Physics in 2011. I'm the only author on that. But it's also featured in this review article by Agarwal and Peters in Advances in Chemical Physics, which should come out in 2013. And I want to emphasize that this whole story is really one of many ways that solute precipitate nucleation differs dramatically from single component structural transitions that have been so widely studied in the past. And of course, because solute precipitate nucleation has so many applications, I think this is potentially a very fruitful direction for future research. A lot of things about this story are incomplete. I've shown you a deterministic model, but of course nucleation is a stochastic process. All we can get from deterministic models is a definition of the dividing surface. We can't get a rate constant expression for how fast that dividing surface is crossed. So all of that work remains to be done, and I look forward to hopefully seeing that this little story inspires some work in that direction.